Are you ready to do some example problems with me? Well, I hope so, because that's what we're going to focus on. I told you it was coming in the last video. So I asked you to write down these examples and then take a stab at them. And then draw the cis and trans form for the following compounds. And then come back and press the play button. And hopefully that's what you did. So that way you can check your answers. All right, so this is where we left off. And we're going to start off by answering the very first one. So 1-ethyl, 3-methyl, cyclobutane. So they want me to clearly show the cis and clearly show the trans. The reason that this compound has a cis or trans, well, first, it's an alkane. How can this be? Well, it's because it's in a ring. Cyclo groups are ring structures. When ring structures happen, folks, they are locked into position. There is not free rotation about the bonds anymore. So there's my cyclobutane. But, of course, means 4. There's the skeletal structure for cyclobutane. On carbon number 1, I'm just going to put that one here. I've got an ethyl group. So ethyl's 2 carbons, right? So 1, and then let's kink it this way, number 2. And then on the 3rd carbon, so if that's carbon 1, carbon 2, carbon 3, we have a methyl group. So that's 1 stick and a dot. There we go. There's 1-ethyl 3-methyl cyclobutane. If I had asked you to draw the structure on a previous test, this is what you would have told me. And I wouldn't have had to ask about cis, I wouldn't have had to ask about trans, because it was something that we had not really talked about and stressed up until this point. But this particular problem says draw the cis and trans form both. So I know I'm going to have to represent them 2 ways. So I'm just going to go ahead and repeat what I did. There we go. So over here to this side, let's make this one cis and let's make this one trans. How can we do it? We just learned about it, folks. We just said you can go in and take a wedge and shade it in or put some dashes in, and that will tell you how to draw the stereochemistry. Well, cis means the same side, right? Okay, well, here's the stick. There's the bond that connects the ethyl group. And we said we will change this to a wedge. And let me just draw it in a solid way. And then this is a wedge. So let me just shade it in solid. And folks, there you go. That's all we got to do. That was hard, wasn't it? So hard. Well, I could have also done them both dashed. It wouldn't have mattered. They still would have been cis. They would have just been pointed away from me instead of toward me. That would be the only difference. So either route is okay. If you put the dashed wedges here, you got a correct answer. Now the trans is as easy. The trans means opposite side. All right, so there's the wedge that goes out to that carbon that has the ethyl group. And here I'm just going to put a dashed wedge. And then on this one, there's the wedge there. And I'll shade it in. And folks, that means they are pointed in opposite directions. And because they're pointed in opposite directions, they are trans. So that is trans 1-ethyl 3-methyl cyclobutane and cis 1-ethyl 3-methyl cyclobutane. All right, so the next one is 2-methyl 3-heptene. All right, so heptene is 7 carbons. 1, 2, 3, 4, 5, 6, 7. That's how I'm going to start this. On carbon number 3, I have the ene group, which is my double bond. So 1, 2, 3, there's my double bond. And then on carbon number 2, I've got a methyl group. So there we go. So I'm going to redraw this, and I'm going to put a focus on the C double bond C, the alkene part. I know I'm going to have to draw 2 of them, a cis and a trans form. So I'll draw the first one up here. There's the legs to the alkene. That's kind of what we've done before. On this particular carbon, I've got this isopropyl group, and the other one that's not drawn is a hydrogen. All right, so there, and then the other one will be a hydrogen. So that is the particular carbon to the left-hand side. All right, to the right-hand side, that carbon, well, that represents this one. And off of that carbon, I have 3 more, right? All in a straight line. 1, 2, 3. And then that 4th bond that's not drawn, it's understood to be a hydrogen. So I'll draw that one in. Well, if I take a look at what I've just drawn, is this cis or is this trans? Well, cis and trans has everything to do with the hydrogens, right? So here's the hydrogen that's pointed down, and there's the hydrogen that's pointed down. They are pointed in the same direction, folks. If they are on the same side, then this is the cis molecule that I have just drawn on a sheet of paper. Well, if I need to draw the other one, it's fairly easy after this point. The only thing that I have to do is target one of the sides, sorry, that's a carbon, and flip that particular side. Just one of them, not both, because then you end up with it again. So I'm just going to pick one side only, and I'll put the hydrogen up there, and then here I'll draw the 3 carbons out. Once more, I'll look at the hydrogens. This one's pointed down, and that one's pointed up. Well, they're on opposite sides, so this is the trans form of that molecule. All right, so that was very traditional. It was what we saw in the alkene world, and now they've just taken this topic and they've just kind of highlighted it once more, so that way we can tell ourselves, don't forget about this. This is called stereochemistry. This was part of what we did back in the day, and it's coming back all over again. All right, so that type of example was not a new example. That's something that we have seen before over and over in a previous lecture module. Okay, let's look at another one. 1 bromo, 4 chloro, cyclohexane. So there we go. There's our hexane. Now, there's a way that we could draw this. We could go through and give me this type of structure again and fully show the axial and equatorial bonds. All right, so let's do it. Just to kind of rehash, just to review. 1 bromo, if this is my 1 position, well, bromo and chloro, they prefer equatorial, not axial. Equatorial's a little bit more stable. So if this is the equatorial, let's say this goes down, this one goes slightly up. So this is carbon 1, carbon 2, carbon 3, carbon 4. So slightly down, slightly up. Slightly down, slightly up. All right, so there is my 1 and there is my 4 position. So they're both equatorial, which is the most stable. And then on carbon 1, I have a bromo. And on carbon 4, I have a chloro. All right, well, if I take a look at what I just did, this is pointed down. This one's pointed up. So in this version, folks, this is the trans version. Well, I could also do a cis form. That's okay for me to do. Let's do it. So if this bromo stays where that's at, right? I told you, cis and trans, you target 1 and that's it. This is pointed slightly down, slightly up, slightly down, slightly up. We already know that if this points down and that points up, that's the trans. How can I make this the cis? Well, on this carbon, this axial bond points down, and that bromo points down. So if I draw that chlorine on that axial bond and not the equatorial bond, then all of a sudden I have the cis form of the molecule. They are pointed in the same direction, and they're both pointed down in that scenario. So that was the old school way that we talked about drawing these cyclohexane structures way back when, right? Well, now we know that there is a shortcut method in a way. Cyclohexane. How else can we draw this? Well, let me show you. You might like this a little bit better. And you might be like, well, why didn't you show me this way back when? And that's because you got to learn how to do the chair conformers, all right? So here's my cyclohexane ring, 2 of them. 1 cis and 1's going to be trans. one bromo, there it is, carbon 1, carbon 2, carbon 3, carbon 4. Right here, this is my chloro group. All right, so there's bromo, and this is chloro. Remember, they're not constitutional isomers. They are configurational isomers. So bromo and chloro in spot 1 and spot 4 in both cases, I need to represent one as cis, and I need to represent one as trans. How do we do it? Let me show you how easy. I'm going to take one of these. I'm going to turn it to a wedge. I'm going to fill it in. I'm going to take this other bond, turn that to a wedge. I'm going to fill it in. What do you think that one is? They're both pointed in the same direction. There's the cis form. Isn't that much easier than this one down here at the bottom? I think so. Very quick, very easy. Didn't have to think too much at all about it. Just draw the wedge and fill it in. That's all you got to do. All right, so how do we do the trans one? Do the same thing. Turn it to a wedge. Turn it to a wedge. This one, we'll fill this one in solid. This one, we'll fill this one in with a dash. They are pointed in opposite directions. Bromine is pointed toward me. Chlorine is pointed away from me. Because they're pointed in opposite directions, one pointed up, one pointed down, this is the trans form of 1,4 or 1-bromo 4-chloro cyclohexane. Wasn't that so much simpler? I mean, imagine if this was your first introduction to cis and trans when we talked about ring structures a while back. I think you would have preferred this way a little bit better. Now let's look at our fourth example, our last one, which is 1,3-dibromo cyclobutane all over again. All right, so cyclobutane, there's 4, there's 4. On my 1,3 position, here it is, there it is, here it is, there it is. I have a bromo group on each side, there and there, and here and here. Okay, no big deal. We'll do this one like the first one. There's no changes in it. I put my bromo groups there. I need to show that these bromo groups are pointed in the same. So just to change things up a little bit, I'm just going to draw a wedge. I'll draw a wedge, and I'll put dashes here to show you and prove to you that that is okay to do. They are both pointed in the same direction. That's all that matters. If they're both pointed in the same direction, folks, this is the cis form that I've just drawn. Now, I need to make sure that this one's pointed in opposite directions, right? So one of these will get maybe a dashed, and one of these will get a solid wedge. They are now pointed in different directions. One pointed away, and one pointed toward me. Because of that, this is the trans form of 1,3-dibromocyclobutane. Folks, if you can do this, then you really do have a comfortable initial hold on stereochemistry. You really do. So good job for you if this was okay with you, because that means that you did your dirty grit work much, much earlier on in previous lecture modules. You became comfortable with cis, you became comfortable with trans, you became comfortable with nomenclature and being able to draw a molecule based on that name, and all of that is fundamental to these types of problems. So if you went through these without a problem, good for you. Your hard work is halfway done. If you struggled with these, you probably struggled with them before. Now they're back to bite you in the butt. Well, now's your chance to show it who's boss. Now is your chance to prove these organic problems that you're not going to take it from them anymore, and you're going to stand up for yourself, and you're going to answer these problems the right way. And this is the first step toward that path. Something else I want to say to you. We're talking about cis and we're talking about trans, and very often we're so focused on hydrogen, same side, different side, same side, different side, right? That's all that drives cis and trans from each other. But I also want you to know that they are different compounds, and they do have different properties that are associated with them. They're the same number of carbons. They're the same number of hydrogens. They're the same number of all the atoms. They are connected the same all the way throughout the molecule, except just how they are oriented in a 3D world. That's the only difference. And just because of that simple little property switch, here you go from cis and you go from trans. Look at the mu. The mu represents polarity or dipole moment. This one, 0. This one pulls at the same amount that this one pulls. So the polarity of this molecule cancels each other out. However, this one does slightly have a dipole moment. This CH3 and carbon, there's your electronegativity polarity difference. Over here, you got the same type of bond pointed in the same direction. Well, because this one's pointed this way and this one's pointed that way, overall they kind of go this way, right? Well, that leads to some polarity differences. So even though this is the same molecule, with the same formula weight, with the same carbon, same hydrogen, same everything, they're both alkenes. No difference other than cis or trans. One of these molecules is basically nonpolar, and the other molecule has some polarity that's assigned with it. In addition to that, look at the boiling points. The boiling point here, 0.9 degrees, and the boiling point here, 3.7 degrees. So they do have a slight difference in even their boiling points, even though it's pretty much the same molecule, just oriented in a different way. That's the only difference here. The same thing's going to happen over here to the right-hand side. On the right-hand side, we have the cis and we have the trans. I know this is the cis because of the wedges. I know this is the trans because of the wedges. And if you look at these boiling points, guys, there's almost a 9-degree difference here, right? Maybe 10. 99.3 minus 91.8. That's a fairly large difference that we can separate in a laboratory using a process like fractionation or distillation. I just need to take it a little slower and give these two things time to separate from each other. I can do that with nothing more than a little bit of heat. Once again, though, it is a ring. It's the same number of carbons. It's the same number of hydrogens. It's the same groups on the rings. They are just pointed in different directions. And just because of that, it affects the intermolecular forces between the molecules. Those intermolecular forces sometimes maybe are not as strong or as weak. And it begins to change properties like these boiling points and like polarity does. All right, so with that said, that's where this video is going to stop. So we need to move on. There's other things that we need to talk about other than cis and trans. So I don't want to waste any more time on cis and trans. I think we've given enough attention already. I mean, we gave it attention way back in the day. We're giving it attention now. Why does it need any more? Cis and trans has had their day, right? They need to just move on. Leave us alone. So now we need to work ourselves into the newer parts of stereochemistry. And that's where this lecture really does kick in with new material. So in the next video, that's where we'll pick up. So come back and see what I've got in store for you.